Welcome to the day 2 video for our unit on kinetics and equilibrium. I have the essential ideas, 3 of the essential ideas posted at the beginning of this. They're remarkably similar to what you saw in the day 1 video. The emphasis of this video is doing much of the same things but for a chemical reaction, whereas day 1 it was the physical process of evaporation. I will read these. Essential idea: chemical kinetics is the study of the rates of chemical reactions, okay? That is how fast or slow chemical reactions occur. This understanding includes factors that can affect reaction rate. So we looked at changing temperature and how that affected evaporation rate. In this video, we'll have a chance to introduce the idea of how the concentration of reactants will affect reaction rate. And there were graphs that accompany this as well. Second essential idea, the reversible process, which again we saw in the day 1 video as well, is a process in which the conversion of reactants to products and the conversion of products to reactants can occur simultaneously. So we'll need to create the condition for which that can happen. And in reversible reactions, the reactants and products are never fully consumed. We'll see that. Last essential idea is that a chemical reaction is in equilibrium when the concentrations of reactants and products are constant. That is, their ratio does not vary. And with that last essential idea, I have said that in day 3 we're going to improve our vocabulary and actually talk about dynamic equilibrium, not just calling it equilibrium. And in day 3 we'll explain why we call it dynamic equilibrium. All right, and the image on the bottom is just an example of the reaction of nitrogen gas and hydrogen gas. It's a reversible chemical reaction forming ammonia. And when done in the proper conditions, the ammonia can decompose into the nitrogen and hydrogen elements. Okay, so here we have the reaction of nitrogen gas and hydrogen gas to form ammonia. I will note that this is an unbalanced chemical equation. What I should have done is put in a coefficient of 2 in front of the ammonia and a coefficient of 3 in front of the hydrogen to balance it and to show that one nitrogen molecule reacts with 3 hydrogen molecules to make 2 ammonia molecules. So for this reaction, as it's expressed in the equation, it looks like it's just a forward reaction. It's just going from reactant to product, the one-way arrow. And we could have that if we introduce nitrogen and hydrogen in an open container. So what we would see there's no lid on this, and on this left container we've got a certain amount of nitrogen and hydrogen placed in that container. Now without the lid on, those molecules are just going to start to mix with the room air. Now under the right conditions, some of them will collide in the right way, and I'm going to circle 3 hydrogen and 1 nitrogen molecule and say, oh, well, those happen to collide in the right way, and they formed 2 ammonia molecules. And then it looks like I've got 2 more ammonia molecules on the right side. So that means as these gas molecules on the left were dissipating, there was another opportunity where 1 nitrogen and 3 hydrogen combined to form those other 2 ammonia molecules. But the ammonia molecules are not going to break down into nitrogen and hydrogen. As they're formed, they're leaving the container. No products are getting built up. They're just mixing with the room air. What we want to do is we want to do the same reaction in a closed container. So reading: a reversible process is a process in which the conversion of reactants to products and the conversion of products to reactants can occur simultaneously. Now we see in this equation here nitrogen gas plus hydrogen gas forming ammonia. In the bottom here, it's got that double-headed arrow. We were first introduced to that in the weak acids of the acids and bases chapter, and we also saw that in our day 1 video where we were looking at liquid water forming gaseous water, and when done so in a sealed container, the gaseous water could become liquid again. So it's the same thing here, it's just for a chemical process. So we're going to do the same reaction above, but we're going to do it in a sealed container. So what I have here is I have 6 images of the reaction happening. So let's call this first one T equals 0. And we're just getting started. So at T equals, we'll call it T equals 1, we've got 2 ammonia molecules forming. Now, I also want to present the idea here that the concentration will indicate the speed at which the reaction's happening. So when it first starts, you can see we've got the highest concentration of nitrogen molecules and the highest concentration of hydrogen molecules. So we're going to say there for those first two ammonia molecules to form, it only took a second. But I want to be creating the image that the reaction slows down as time goes by, as the concentration of reactants decreases in that container. So I'm going to mark this one, slide 3, as time equals 2.5 seconds. And so now I've got 4 ammonia molecules, the 2 that formed in the first second, but now it took 1.5 seconds to make the next 2. And then in the fourth slide, we've then got 6 ammonia molecules. So I want to leave you with the impression that the reaction is not occurring as fast. So if it took 1 second to form the first 2 and 1.5 seconds to form the second 2, I'm going to say that this third one is at time equals 1.5. So we want to say 2, so we'll say 4.5. And what I've done very deliberately here is I've made these last 2 slides the same as the t equals 4.5 one. And that is to say that the reaction is really slow to the point that that equilibrium has been achieved. So these might be at t equals 7 seconds and t equals 10 seconds or something like that. So we had the rapid growth of ammonia early on, and then it continuously slowed through the process until we achieved equilibrium. You will notice that at this point in the reaction, the concentrations of the reactants and the concentrations of the products are now constant in there, even as time goes by. So in this last image here, it says chemical kinetics is the study of the rates of chemical reactions. That is how fast or slow they go. And whereas in the day 1 video, we had a reason to talk about how temperature affects reaction rate, here we can talk about how concentration affects the reaction rate. So if we were to graph this 6-slide image above, but think of it more continuously, you can see that we're starting with no ammonia in the container, and we're starting with, we'll say, the full amount of hydrogen and nitrogen. And as time goes by, initially you're rapidly forming ammonia, and you're rapidly depleting the hydrogen and nitrogen. But the rate at which the reaction can occur is a function of the concentration of the reactants. So as you deplete the hydrogen and nitrogen in that container and build up ammonia, now those nitrogen and hydrogens are having a tougher time colliding to form the reaction. So the reaction starts to slow. So you don't lose the hydrogen and nitrogen as quickly, and you don't gain the ammonia as quickly. And then finally, in what we said on this one, we said it was about 4.5 seconds. Starting at about 4.5 seconds, you just are flat. So you're not making any more ammonia, and you're not depleting any more hydrogen and nitrogen molecules. Those concentrations no longer vary. And that's this part called equilibrium. I'll just write that in there. When the curves flatten. Okay, so reading this last sentence here, a chemical reaction is in equilibrium when the concentrations of reactants and products are constant. Their ratios do not vary. So this is what it looks like in the graph. This is what it looks like in the storyboard, so to speak. Thank you for watching day 2.